A lot of people lose touch with what's actually going on in the computer hardware the higher the level of abstraction you go. So by the end of this video, we will be adding two numbers together using nothing but transistors to show you what's actually going on. Level 1, C. In my terminal emulator, I will simply create a new C file using my text editor. I will include the required headers to print my output, declare an int result equals 2 plus 2, and print out the result. Finally, we can compile and run the program using GCC. And as expected, we get the correct result of 4. But you better get ready, because it's about to get a lot more involved than that, because for level 2, we are going to do the same addition in machine code, so just using zeros and ones. This is ultimately what your C code from step 1 is going to get turned into before the hardware ever sees it. Now at this level of abstraction, working with an ISA manual in hand is mandatory. The ISA is the set of rules that dictate how computer hardware should understand a sequence of zeros and ones. For example, we might use English to understand each other. In the same way, the hardware and machine code must operate using the same ISA to make sense. There are many different ISAs, but today I'll be using a popular open standard called RISC-V. Before writing out the machine code, we must write out the assembly code. Compilers like the GCC compiler we used in step 1 are used to translate the C code to assembly code. Let's look at the manual. There are 3 places we need to look at. The instruction itself along with its corresponding opcode, in this case the add instruction, the instruction format, which is R-type for add, and finally the register file. We simply need to match the numbers to their corresponding positions in the format instruction. The add instruction is going to add the contents of 2 registers with each other and store the result in another register. Registers are temporary storage locations inside of the CPU. In RISC-V, data needs to be moved into registers before we do arithmetic or logic on the data. We can do this by using another instruction called load immediate. We can use this instruction to load an immediate number into one temporary register T0 and another into a temporary register T1, and then add the result and store the values into S0. Converting this into machine code is as easy as matching the appropriate bits to the correct fields based on the ISA. We will end up with the following assembly and machine code. Of course, a machine not following the RISC-V ISA will not make any sense of this. However, we can use this free online tool to verify our results using our C code from level 1. As you can see, the compiler is a lot smarter than us, as it managed to compress our 3 instructions into only one. It realizes that 2 plus 2 can actually be folded into 4 and written as one load immediate instruction. At this level, we are still working in the interface between software and hardware, so we can go one level deeper. Level 3, logic gates. So how does the physical hardware carry out the addition though? The hardware uses mathematical logic gates to do addition. These gates can perform logical AND, OR, and NOTs. These are the same operations you usually write in a higher level language, like inside an if statement in Python. To implement a function, such as addition using these gates, one simple approach is to build a truth table like this. We must work with base 2 numbers. Let's take a look at the example of adding 2 1-bit numbers together. Let's imagine we have 2 numbers A and B, and perhaps we also have a carry in for our addition called Cn. Let's say A and B and Cn are all 0. What should the sum and carry out be? 0 plus 0 give a sum of 0 and a carry out of 0. What about if they are all 1? Then if we do the math using the base 2 numbering system, we will end up with a sum of 1 and carry out of 1. We complete the rest of the table in a similar style. Next, by finding out where our sum is equal 1, we can write out a Boolean expression for it. For example, when A and B and C are equal to 1, we know that the sum is 1. Or it is 1 when A and B and C invert, and so on. We can do the same for Cout. The resulting hardware is called a full adder. We can then build out this circuit in a software like Logisim. However, to add 2 and 2 together and get a result of 4, we need a 3-bit adder, as 4 in decimal needs at least 3 bits in binary to be represented. Therefore, we can connect many full adders together like this in a style called the ripple adder. Finally, we can set the inputs as 2 and 2, and we will have 4 in the output as expected. Surely this is the closest to the hardware we can get, right? Level 4 transistors. Doing the addition using transistors is the closest we are going to get to the hardware. You can think of transistors as voltage controlled switches, although the real physical process behind it is quite simple to understand, so I recommend you look it up. There are many different types of transistors. The ones we will be using today are called MOSFETs. Without going into too much detail, there are NMOS and PMOS MOSFETs. What's important for you to know is that they act opposite to each other. If a specific voltage switches an NMOS on, for example, it will switch the PMOS off. Using this idea, we can combine them both in this manner in a pull-up and a pull-down network. This technique or technology is called CMOS. What I have made here is a NOT gate or an inverter. Notice that when the voltage at the input is high, the NMOS will be on, and the output is pulled to the ground, so I will get 0. Remember I said the PMOS acts as the opposite, so here the pull-up branch or network will be off. When the input is low, the opposite occurs and our output is pulled high. Therefore, we have built a NOT logical gate. Using the same CMOS technique, we can create an OR and an AND gate, meaning we can recreate our exact setup from the previous layer of abstraction using transistors. Notice that using CMOS, we actually build NAND and NOR gates and invert the output by adding another inverter. I am only going to add two 1-bit numbers together here, as scaling this in transistors gets a little convoluted. However, looking at the output waveforms after the simulation here, it appears we have achieved our purpose. For example, when we add 1 and 1 together, we get 1 in the sum and 1 in the cout, as expected from our truth table. I hope this video really helped to demystify how computers actually work under the hood. At the end of the day, it's all a physical process that scales up through many layers of abstractions. We can honestly go even further and discuss the actual underlying physics behind the transistors, but I hope this video gave you a general idea. I will put further reading resources and references in the description of this video if you wish to dive further into any one single topic.